Hi, my name is Sam Lee, and today I will present Lab 4 Oscillations. The goals of this lab are to first observe the motion of a spring mass system where the spring is oscillating up and down and the mass is swinging on the spring in a pendulum motion. We'll use tracker to determine the position data of the spring mass system, and we'll then use GlowScript to create a computational model that predicts the motion and also computes the changes in energy of the spring mass system. We'll then compare the observed motion from tracker and the predicted motion from the computational model. And lastly, we'll study the energy model from GlowScript to see if the energy principle holds. The fundamental principles we'll be using in this lab are Newton's second law, which is delta P over delta T equals F net, Hooke's law, which is Fs equals negative Kx, and the energy principle, which is total energy is equal to change in kinetic plus change in gravitational plus change in spring potential energy. So in tracker, the first thing I did was set the origin point of the spring as the origin point on our tracker model. And then I set the length of the spring to 0.7 meters. This was all given to us by the lab. And then I plotted each part of the spring, or each part of the spring's motion per frame. And I ended up with an oscillatory graph. So the data I got was that the mass was 0.402 kilograms. This was given by the lab. From tracker, I got that the starting time was 0 seconds. The ending time was 9.23 seconds. The initial position was negative 0.125 in the x, negative 0.731 in the y, 0 in the z meters. Initial velocity was 0 all around. K, which is the spring constant, is equal to 6.83 newtons per meter, and L naught is equal to 0.123 meters. These are both given by the lab. So the first thing I did in GlowScript was plug in the initial conditions I got from tracker. So that's 0.402 kilograms on the ball. And then I plugged in the position vector and the velocity vector, the spring constant, L naught, and also the time frame in the while loop. Next thing I did was bring in our physics principles. So I changed the equations for K equals 1 half mv squared. Potential G is mgh in the y direction, and potential spring is a half ks squared. And then total energy is just equal again to change in K plus change in UG plus change in US. F grav is negative mg, F spring is negative kx L hat, and then F net is equal to F grav plus F spring because those are the only two forces acting. And then I added the momentum principle, which is Newton's second law, and then I changed the values for L hat, change in L, and then I added the delta potential energies. The first graph we got from GlowScript was a graph of the predicted motion versus the observed motion. The blue represents the predicted motion from the computational model, and the red represents the observed motion from tracker, the position data. And so as you can see, they're very close together. This is a good thing. That means we did our lab pretty accurately, and that the computational model using the physics principles matches very close with what we ended up with in our observed position data. The next graph we got was the graph of changes in energy. So the blue represents change in K, red represents change in UG, green represents change in US, and orange represents change in E. The most important part of this graph is that change in E, the orange line, stays at 0 pretty much the whole time. And that's good because that means our energy principle holds. Change in energy is 0, which is a good thing because in the closed system, change in total energy should remain 0. The next thing we did was compare the oscillatory period in the x versus the y. So for the x, I averaged up all the periods and ended up with 1.667 seconds, and the y I did the same and ended up with 1.5 seconds. And they're pretty similar, but they're also a decent amount different. And I think the reason for this is because in the x direction, the oscillation is based on a pendulum, In the y direction, the oscillation is based on a spring, and both of those have different equations or ways of computing them. Thank you.